Hi, this is Yifei Yuan from Alibaba Cloud. I'm very excited to share with you a new network verification approach called Relational Network Verification for validating network changes. This is a joint work with Xiang Xu, Dakari Kincaid, Arvind Krishnamurthy, Ratu Mahajan, David Walker, and Anand Jai from University of Washington, Alibaba Cloud, and Princeton University. Making changes to a running network, such as replacing routers, updating configurations, is one of the most risky activities in network management. As you can often read on headlines, when implemented incorrectly, even simple network changes may cause severe outages, making businesses unavailable and causing millions of dollars of losses. At Alibaba Cloud, according to our internal statistics, configuration changes alone account for 56% of total network outages, making it the #1 root cause for network outages. In the last 10 years, there has been remarkable progress on network verification research. Typically, existing verification tools can verify whether a single network snapshot satisfies a spec, such as DC1 can reach DC2. We call them single snapshot verification. However, applying those single snapshot verification abstraction to network changes is challenging. One of the key reasons is a lack of precise specification. To illustrate, let's consider a simple example where the operator wants to make a change so that traffic on path ACD in blue will be shifted to the path ABD in green. And meanwhile, the forwarding path of other traffic should not be changed. Specifying those change intents precisely in single snapshot verification abstraction may require us to specify the desired path for each traffic class, which is hard in practice. For example, to specify the first intent, we have to discover all traffic classes on the path A, C, D, and then specify that each of them traverses A, B, D after the change. Specifying the second intent is even harder. In addition to discover all other traffic classes, we have to discover all their current paths and specify that each of the traffic classes still follows the discovered current path after the change. This kind of spec is infeasible for real-world networks, since its size is proportional to the entire network size, which is huge. For example, our global WAN has more than 1,000 routers and millions of traffic classes. Sometimes the operators don't even know the precise path for many of them. Today, our operator mainly rely on the following inspection process. First, they use a simulator called Huoyan to compute the forwarding path of all traffic classes for the snapshot before the change and after the change. We call them the old path and the new path, respectively. Second, they compute the differences between the old path and the new path, or path diff, for each traffic class, and manually inspect if any path diff for any traffic class is incorrect. The good thing about this approach is that operators not only need to focus on the differences of the path, making it possible for manual inspection. However, this process is still time-consuming and error-prone. A typical change may have tens to thousands of differences, but an experienced operator may only analyze tens of differences each day, making it weeks in total to check even simple changes. Let me show you a real change example on the global WAN at Alibaba Cloud to further understand this challenge. In this example, we have two ASs, AS1 and AS2. Each circle here represents a group of routers that serve the same role. Circles in the same color represent that they are in the same region. Originally on this network, traffic from DC1 to DC3 is exiting AS1 via B2. The operator wants to optimize the forwarding path such that all traffic from A1 to D1 follows a shorter path, that is A1, A2, A3, D1. Note that the subpaths from DC1 to A1 and D1 to DC3 should stay the same. Meanwhile, the forwarding paths of other traffic should not be changed. In the first attempt, our operator updated the import policy for routers in A2 to allow DC3's prefix, hoping that the traffic will pick A2 as the exit point. However, when manually inspecting the path diff, the operator did not observe the desired change. The rule cause is that B2's import policy assigns higher local preference to the prefix, so that the traffic to the prefix still prefer B2 as the exit point. In real world, similar mistakes are common because real-world networks evolve over time. Having complete information of the network is very difficult. To fix this problem, in the second attempt, the operator makes A2's local preference higher and also lowers the local preference on B2 for the prefix. After inspecting the path diff, the operator indeed observed that the traffic from DC1 to DC3 has shifted from region B to region A in AS1, as shown in the blue path. However, they also found another traffic class from DC2 to DC3 was incorrectly changed, as shown in the red path. Further analysis showed that there was a configuration typo on B2, which caused this unexpected traffic shift. After fixing this typo, the operator runs the inspection again. This time, the operator found that the traffic from DC1 to DC3 is redirected from A3 to B3 instead of going to D1 directly in AS2. Actually, this problem appeared after the previous attempt, but the operator totally missed it due to the information overload. Further analysis showed that due to the large scale of our network, the ISS cost in S2 is not configured optimally, causing the suboptimal forwarding path in S2 as shown on the top. Finally, in the fourth attempt, our operator fixes ISS costs and found all path diffs are expected. In total, this seemingly easy change takes weeks of efforts. Since network changes are so risky but unavoidable, can we make it more reliable, efficient, and automated? Our answer is Rela. Rela is a high-level specification language and a verifier for validating network changes. The design of Rela is inspired by the current manual inspection process and the relational program verification research from the formal methods community. In Rela, network operators write the change specification in Rela's high-level specification language. Similar to the manual process, Rela relies on the simulator to compute the old and the new path for the network snapshot before and after the change. The Rela verifier then can automatically verify if those paths satisfy the specification. Let me first introduce the Rela specification language. The high-level idea of this language is to allow network operators to describe the desired relation between the old and the new path, instead of the absolute path themselves. The atomic spec is specified in the zone modifier pattern in Rela, where the zone is a path set that should be focused on in this change, and we define it in reg expressions. The modifier describes the desired change to the path set in the zone, such as preserve the path set, add or remove some path, replace some path with others, and any path in a given range. Those specifications can be composed using concatenation and the prioritized union to specify complex intents. Concatenation allows us to specify the change relation for subpath. And the prioritized union allows us to specify the if-else relationship. Let's revisit this example and see how we can use RELA to specify the change intent. Recall that the first intent requires that traffic from A1 to D1 to be moved to the path A1, A2, A3, D1. And the second intent requires the path of other traffic to stay the same. For the first intent, at the first step, we can write recursive expressions for each rotor group so that all rotors in the group can be represented. For example, if the group A1 has rotor A1 and A2, we can write a recursive expression as shown on the right. Second, we can specify the change for the subpath from A1 to D1 using the zone modifier pattern as shown on the right. In this spec, since the path set we'll focus on are the path starting with A1 and ending with D1, so we can simply write the recursive expression A1 dot star D1 as a zone. For the modifier, as we want the desired path to go through any path in A1, A2, A3, D1, we can simply use the any modifier to specify that. Next, we can specify the change relation for the full path from DC1 to DC3 using the concatenation composition. The full spec is shown on the right. We use DC1 preserve and DC3 preserve to specify that the subpaths from DC1 to A1 and D1 to DC3 should stay the same. For the middle subpaths, we can reuse the spec defined before to specify the desired change. Finally, we can concatenate all those three specs together to have the complete change spec for intent 1. Now, for intent 2, we need to specify that all other paths should not change. For no change, we can reuse the zone modifier pattern as shown on the right. Finally, we can compose intent 1 spec with a no change spec using prioritized union as shown on the right. This completes the precise specification of this change, which is compact. Now let's look into the RELA verifier to see how it works briefly inside RELA. Given a high-level specification, RELA first translates it into the intermediate representation, or IR. RELA's IR is designed based on the theory of regular expressions and the regular relations, which are extensively studied before and known to have efficient decision procedures. With this IR, RELA combines it with old and the new path and compiles them into a set of finite state automata and transducers. Lastly, RELA checks if a spec is satisfied by checking the equivalence of the compiled finite state automata. You can read the details of the RELA verifier in the paper. In the paper, you can also find extensions to RELA's specification language, such as how to combine it with packet header constraints. We have implemented RELA and evaluated it based on a real-world dataset. This dataset contains all expert-reviewed high-risk changes in Alibaba Cloud's Global WAN from June 2023 to January 2024. Our results show that RELA is expressive. it can specify 97% of the data plane intents in the dataset. Moreover, those specs in Rela are compact. 93% of them can be written within less than 10 atomic specs. Here are some example change specs in the dataset. You don't need to read the detailed spec, but you can see that specifying those real change intents is easy and compact in Rela. For performance, we evaluate Rela on R1, which contains more than 1,000 rotors. Each rotor has more than 10,000 prefixes, and there are millions of traffic classes in total. Our results show that the Rela verifier is efficient. 80% of the changes can be verified within 20 minutes. As a comparison, the simulation itself took more than 2 hours to complete. To conclude, network changes are risky. Existing approaches such as single snapshot verification and manual inspection do not suffice. To solve this problem, our observation is to use relational specification to specify the change intents precisely and compactly. Based on this observation, we propose Rela, a high-level specification language and a verifier for validating network changes. Our evaluation based on real-world dataset show that Rela is expressive and efficient. Finally, Rela is open sourced. Please check it out at this link. Thank you for your attention.